Like 8 sides.
Okay, lesson 3. Lesson 3. It's more about the derivative, okay? We're not learning our shortcuts to 2.5, but it's more about understanding the derivative and how this goes in with linear approximation. So it's still going to be looking at the derivative when we can and can't do a derivative, finding equations, drawing lines, you know. So with that in mind, let's see what it all has to say. There are times when we are interested in finding the effect of small change. For example, how is the revenue at your local theater affected by a small change in the ticket price for a movie? We can explore an application of the tangent line to a function called the linear approximation. And this is where we're going to use our tangent lines here. You've already seen that on a curve, a curve lies very close to its tangent line near the point of tangency. If you zoom in repeatedly on the graph of f at the point, the function will appear to be linear. When you've zoomed in to a sufficiently small neighborhood around the point of tangency, it would be difficult to distinguish the function from its line. This property of differentiable functions is commonly referred to as local linearity. You guys have played around with graphic calculators. You zoom something in far enough, it no longer looks, like a curve. It's just that small piece if it's zoomed in far enough. The idea is if you had your curve graphed and that tangent line graphed, they're going to become the same, okay, in that small little moment, okay? So, I'm going to, all 3 classes had quite a bit of slides today, so I was struggling with getting enough pages available on my limit of 15 here. So let's do some exploring here. Using a graphing utility to graph y equals sine x, let's investigate the neighborhood around the origin. Use the zoom in feature of the calculator at the origin. So, with this in mind, grab your calculator out. Let's do some graphing. Because we haven't used them much lately, have we? Oh no, why did I just clear that? I didn't want to clear that. I'll need that later. It did feel weird that everyone had to grab, actually physically get the calculator out. Like, what? No one has them out? Oh yeah, we haven't really been using them yet. Okay. So sine x. You guys know what sine looks like, right?
Yeah.
So they're asking us to graph sine x. We're going to investigate the neighborhood around the origin. Use the zoom in feature of the calculator at the origin. It says 4 times. So if I use this 4 times, remember, I don't know how much you remember here, but if I go to zoom and I do zoom in, it doesn't zoom in immediately, right? It's asking me where do I want to zoom in at. So just leave your cursor at the origin and hit enter. So there's once. You basically have about a cycle there, right? Zoom in again. Zoom in, hit enter an extra time. Well, shoot, they're zoomed in twice, and what's it look like?
About a straight line.
About a straight line, which it kind of is at that portion if you think about it. I'm going to zoom in. There's 3 times. And there should be 4 times. Is there really a difference between the second, third, and fourth? I'm not sure, not in looks at least. I'm sure there is actually, but okay. So when you zoom it in, you've got something that's looking like a straight line. Okay. First of all, it's asking, can you estimate the slope of this portion of the sine curve by inspection of this window? I don't know, maybe we didn't need to calculate as much as I thought we did, because I guess we do have it up here on the screen, don't we? But, hey, you got to touch the calculators.
Yes.
Huh?
I calculated it won't grab.
Is it paused?
Every time I push grab, it just goes back.
Graph because your snap plots are on. Right. Now you got to graph. Now you just have to type your function back. Okay. Thoughts on the slope? I hope you're not responding to the slope question when you're saying that.
1.
What'd you say?
1.
Maybe. Does it look like you're going up and over about the same?
Yeah, it looks like it might be 0.5.
Well, that's what I was kind of looking at. It looks like if I go up 0.05 and over 0.05, I'm going to be about the same place if I use that, right? So, would you say it appears to be about 1?
Yeah.
Okay. We don't know exactly, but I'm going to say that. Okay. With that in mind, what can you say about the slope of the tangent line at x equals 0 on the function y equals sine x? It would also be about 1. Okay, in other words, if it appears that the tangent line or the actual graph when zoomed in is looking to be about 1, then a tangent line would go right through here. Okay, it would go right through here. So I'm trying to remember what I have written. The slope of the tangent line at x equals 0 is 1 on the curve y equals sine of x. Okay. I don't know that I'm going to write all of that, but slope of tangent line, I'm just going to say slope of tangent line would also be 1. Write the equation of the tangent line for y equals sine x at x equals 0.
Just be y
Y equals 1x. Because we just talked about the slope is 1. And if it's saying x equals 0, well, that's going to be the ordered pair 0, 0. And so that also means if you're at the ordered pair 0, 0, what's your y-intercept? 0. So yeah, you're at y equals 1x. Here, it's mx plus b is what we're doing. So you do end up at y equals x. Now, what can we do here to see the connection? Did you graph it? Graph y equals x.
Whoa. Wait, I'm not ready.
Watch carefully, and I would graph it in a different color than what your current graph is. My line changed colors, that's what I can say.
You go on top of each other.
Did you see it change?
Yes. Yeah.
Now, if I go back to Zoom 6, notice it's not the same graph, is it? It just was at that one little point, at the point of tangency. So, you know, I'm curious, if I do one zoom in, sorry, mine are graphing in order. Yeah, there's a good view right there, is if you just use one zoom in. You can see the idea of, okay, that's point of tangency is there at 1, or at 0, 0, I mean, so slope of 1. Okay. Move to the next page. Okay, we are going to do something I hate doing on the BenQ, and that is sketching tangent lines. You might want some rulers. The rulers will help you greatly, especially because our Rose-Hulman rulers are clear and you can kind of see through them in spots. It's helpful to me, but
Take one, pass it down.
Okay, so in each figure below, use a straight edge to draw a tangent line beyond the point of tangency in each direction. Okay, I have estimates for the slope, and that's what I was looking. It never asked us to find estimates for the slope, did it? I just did. Okay. So, point A, you ready? Did you attempt to draw a tangent line? You want to try in the bin Q? It's 10 times worse. At least you get a ruler. That's my thing, is I don't have a ruler option. Because I have to just freehand. Nope. Huh? Oh, so it's not just me that thinks A is hard? Okay, that's the best I'm going to do. I'm just going to stop there. A is hard. I don't even feel like I have the best possible, I feel like I'm almost a little bit above there. Estimate. Just estimate, okay? Slope of the tangent line at point A.
I said 5. Yeah.
5. Some positive number. It's going to be bigger than 1, definitely, yes, because it's steep. So, approximately 5. Okay. B. Thoughts on the slope of B, of the tangent line at B? 0. Okay. What's happening here? What is point B? A maximum, yes?
Nice.
Okay. We will learn the slope at a maximum. The slope of the tangent line is always going to be 0, so that's helpful because that means the derivative at that point will always equal 0. Okay? I heard negative. I agree at that point.
-2. Yeah, for sure.
I still don't like it. My answer key has -2, so I'm definitely willing to go with it. Again, it's difficult, isn't it? Okay? Don't stress about if your line doesn't have that same slope. Not a big deal. Okay. Let's continue.
Wait a minute. How is that possible?
So A.
Does a straight line only touch a point once? That's straight line.
Okay, so remember that definition was slightly off, though. Because remember we had, and I don't know if we have any here, tangents where they also went through the curve somewhere else. Okay? So I'm trying to remember, we need a better definition of tangent line, but that's the definition we learned back in geometry, right? Or at least, I always think about. But yeah, so your tangent line for point A is the line that goes through point A. Okay? And I guess it comes down to for what we're trying to do. Okay? We're trying to figure out the slope of the curve at that point. And the slope of the curve at that point is equivalent to the slope of the tangent line. Well, we don't even really need a tangent line here to do this slope, do we? So what is our slope?
-2.
Okay. Rise -2, run 1. What about B?
Oh, man.
0.
What'd you say? So I'm hearing 0.
You're gonna tell me it's not 0.
What?
How?
It's not possible.
Why?
Is it?
Yeah, I don't know.
D and E does not exist. No, it's right there.
It's right.
No way. It's right there. I can see it.
I know it. It's a fill.
So, okay. What's different about this point B to the last point B?
It's not a curve.
It's straight.
Not a curve. It's a sharp point. Okay? And so,
Triangles.
because it is a sharp point, you cannot do the derivative. Okay? You can't have the slope of a tangent line. Okay? You can't have a tangent line. Okay? It would be a teetering line. It wouldn't have a spot to rest. It's more like a teeter-totter. Okay? So, it's a sharp point. It doesn't work as 0 because it would be teetering. And here's the deal. Remember when we talked about, I'm trying to remember how we did this, but wait a minute, it would, wouldn't it? Why does that statement in my notes not make sense? The limit as x approaches 0 from the left. Why do I have written? Doesn't make sense. Sorry, I'm struggling with, I have written in my notes, and did I miswrite or am I forgetting something? The limit as x approaches 0 from the left does not equal the limit as x approaches 0 from the right, but it does. They're approaching the same point, aren't they?
Yeah.
So the limit exists.
What would it count?
But again, it comes down to it doesn't work as 0. It's the whole, it would be teetering. It wouldn't be set on a curve. Okay? Now, what's the piece to learn here? Whoops. Oh no. Oh my goodness. Well, I hit back page instead of undo and erase. So every time I go back a page randomly, it's because I mean to hit erase, but instead I hit back. They're both arrows. I know, bad excuse, but. Okay. So, lesson to be learned. That's part of our lesson today. You cannot, at a sharp point, a hard point, a cusp, you cannot do the derivative there, okay? That is what we call not differentiable, and you cannot do the derivative. What about C?
2.
Okay. The derivative of a straight line is just the slope of the straight line. Are we learning some stuff? Okay. Ready for part C? And this is where I hesitate to say, a tangent line, touches a curve at one point. Well, in that area, I guess. But okay, what's going on with A? Slope at A.
Negative.
I was getting ready to say disagree. I can agree with negative 1/2. Are you guys good with negative 1/2?
Yeah.
And again, no stress if it's, slightly different. Obviously it has to be negative. Okay. What about B?
Zero.
Does not exist.
The line
it's not. It's not.
It's not a sharp.
Technically, it's not.
It
Sharp.
is.
It's
It's
curved.
going like this.
Yeah, but it's
But if you
curving.
zoom in,
But it's curving into it.
It's going like
It's
this.
a little curve.
It is still
What? No.
Take it.
But it's curving.
okay. So B is what I would call a cusp. Okay, because I guess maybe that's, I don't know, hard point, a cusp. They have a very similar definition, but maybe it's more of a cusp because it does curve into it. But here's what you have to go with. It's still not a curve.
So it has to be a visible curve.
It has to be a
To
curve
be anything.
to have to be differentiable, to have a derivative.
Can't move. It's gonna-
Okay, so it's got to be a curve. Whereas I get what the idea that without that point here, it would do something like that. That's not a curve. That's a sharp point. Okay.
Yeah.
Thoughts on C?
One and a half bottom.
Even without drawing the line, it's going to be the opposite of A, isn't it? Something along those lines.
Okay.
Okay.
Check your one.
On D, we only have A, correct?
Yeah. Trick question. No slope.
Can't
D.
What's my tangent line going to look like?
exist.
Straight up and
No
down.
way. Yeah, it's gonna touch.
Okay. I mean, there is a tangent line here, but it would be a vertical tangent line. What's the slope of a vertical line?
No, it's 2.
No,
Like it's whatever point it's on.
no,
Oh,
no.
never mind.
Slope of a horizontal line is 0 because we think like 0 divided by, like if you think rise over run, rise is 0 and runs however many. So 0 divided by 3 by 5. For a vertical line,
Divided by 0.
it's however much you rise divided by 0 is a run, and you can't divide by 0. So we're going to put D and E. When we talk about the slope of a vertical line, you usually hear it said as undefined or no slope. Undefined is more the calculus terms of what type of slope there is, but we're going to use D and E because it's the idea that it is not differentiable. Okay, and here I'm going to say cannot exist when tangent is vertical. Okay. Okay. You learned a little bit, right? Okay, let's work to fill in these blanks down below. The position of the tangent line relative to the function it models depends on the concavity of the function at the point of tangency. So the idea of whether a piece of the graph curves up or curves down will determine where that tangent line is, whether it's above the curve or below the curve. Okay. Throughout this course, you'll be required to explain, justify, and defend your knowledge using proper terminology and precision. Use the graphs from example 2 above to complete the following statements. Okay, so when the curve is concave up, the tangent line lies where? So first of all, we haven't really talked about concavity, have we? Or do you know concavity?
You said it, but I don't really.
Okay, so a curve that is concave up is curving up. Okay, now something like, okay, that's concave up too. okay? But it's the idea that it's bold upwards, if that makes sense, okay? If it's concave up, it's gonna catch the rainwater, okay? With that in mind, when the curve is concave up, where is the tangent line? So if we're concave up, we don't really have good concave. Do we have any concave up? No. Okay. So, but the idea is, if you look at this parabola, all those tangent lines would be below. Yes. So I have below the curve in my blank. When the curve is concave down, okay, anything now concave down, if we talk about having concavity, it opens downwards. So now it's bold downwards. Okay, your cereal bowl is flipped upside down now. What, you know. So now the tangent line on these lies above the curve. This is what happened on example A, yes? All these tangent lines on the parabola were above the curve. On C, the two we were able to draw were above the curve. Okay. At a turning point. Wait a minute. At a turning point, max/min, the tangent is blank or blank. Wait, what? I don't like the way that's set up. Okay. But at a turning point, in other words, and specifically they're referring to max and mins. What do you know about your tangent there? It has a slope of 0, and what kind of line is it? Horizontal. So the blanks are filled in as 0 or horizontal. Not crazy about how those blanks are set up, but that's right. At a point of inflection, concavity changes. The tangent is blank. Point of inflection where the concavity changes. So if we go back to some of these. D, we have concavity changing, yes, because right here on this left piece, right now I'm concave up. It's facing upwards, and then what happens here? Now it's downwards. Concavity changes. Technically, concavity changes here on C also, because on this first part you're concave down, then after the cusp, well, no, it doesn't change, does it? But it's a different, I mean, there's a break in the concavity, I guess. It's not continuous concavity, but okay. But anyway, so D is our example here. When that concavity changes, we had a, what type of tangent line? The vertical line. So, yeah. She has this set up as vertical on this blank. And then I did kind of try to draw something in here. So you kind of have the idea of, you know, that's the idea of what we're talking about there. Okay. At a sharp corner or cusp, the tangent does not exist. The one that is making Tate so mad. Caitlin too, I think. I don't know. Maybe a little bit of everybody except Aiden.
Made me mad the first time, but no.
At a point on a linear function, the tangent is it's going to have the same slope, isn't it? Yeah, the same slope as the line. Okay, because this was it B? Yeah. When you're talking about the tangent line, it is the same line. So we're talking same slope there. So I've written on mine the same slope as the line. Okay. Continuing. Or not. Holy cow.
Is this a breaker?
I don't have it as that in my notes.
It might be though.
I don't have time for that this week.
No.
Please, better crank cows. I know it's tomorrow.
Okay. Tomorrow we are going double speed, I guess.
No. No.
Or I'm wondering, I haven't looked yet, are there things I've maybe skipped?
No.
Okay.
Holy smokes.
Okay. Yeah. Although technically my watch only says 12:29, so I do still have some time. But you guys are like, no.
I need to close my book. It's taking so long to find it.
Where's Tate's name? I don't understand. Wait, that's what Logan.
I think it's a double one.
Logan is saying. Oops.
I think I kind of put you, I had to put you guys as kind of double up. Okay. Reading. Okay, yeah, we got a lot to do tomorrow. That's all there is to it.